Today we are going to do a composition of functions lesson. This is lesson 7 in our unit 1. These are the new notes. There is a video posted from an older notebook that teaches the same concept but just has different examples. So composition of functions, if you think of music and composition or composing, we are putting things together. When we are looking at composition of functions, we are looking at two separate functions, f of x and g of x, in which the output of one function is used as the input for another. Essentially, we're bunny hopping these functions. For notation, you will most often see this means f, that depends on g, that depends on x. So f of g of x. Another notation that you will see is this open circle. This is not times, not times. We're not multiplying these two functions. We're putting one inside of the other. So for example, if function f is a linear function like 2x minus 2, and function g is a quadratic function like x squared plus 3x, then when we look at the composition, we are putting g, the entire function g, in place of x. So we're putting it inside of f. So originally f depended on x. We are replacing x with function g, and we are substituting it into f. So now instead of a linear function, we end up with a quadratic function. So this is where the original x used to be. And then you can distribute and collect like terms and simplify if you want. But this is just the concept that we're working on today. So the output for G becomes the input for F. So we start with X's and we put them into G, and G spits out some Y values. So right, that's our output. But then we're taking these values and we're putting them into F. So the range of G of X becomes the domain of f of x, because we're putting we're putting one function inside of the other. All right, so to determine the equation of the composition function, we substitute one into the other, and then we simplify. So just as before, if we have the function f, we put g inside of it, right? We are substituting the original x with the entire function g. We distribute and collect like terms, and we end up with a composition function. You can do this in any order. Sometimes the question will ask you, what is g of f of x? Meaning, what happens if we put the function f into the function g? Now remember, let me just go up here. G had two x's in it. It had an x squared here, and it had a 3x here. You're replacing every single x with the new function. So when I go do it backwards here, put f inside of g, then I'm going to have the f in two different places. So f squared plus 3f. And then again, expand, collect like terms, simplify where necessary, and note that the order totally matters. Which one is on the outside and which one goes on the inside. This is not the same as that. So this is what we're working on. We're going to look at what do the functions look like. We're going to work on perhaps what is the domain and range. Do we need restrictions in order for this to work? And so on. So in example 1, we are given a function f that's linear, a function g that's quadratic, and we are asked to find three things. What is f of g of 2? What is g of f of -3? What is g of 1? So it's possible to put one function inside itself. So to determine these values, we look at the inside function. So looking at A here, A asked us for f of g of 2, means we are starting with x equals 2, we're putting it into g, and whatever number we get out, we're then going to put it into f. So g is x squared plus x, so this is 2 squared plus 2, which is what, 4 plus 2, this is 6. So g of 2 is 6. I'm putting g of 2 into f, which is the same thing as evaluating f at the number 6. So this is 4 minus 6, which ends up being -2. So the composition function f of g of 2 gives me a final output of -2. For example B, same idea. We start with, I suppose, method 2 is doing the direct substitution, means finding what is the composed function first. So if we had f of g of x, you could do the composed function first, rather than doing what's the inside function, evaluate it, and then putting it on the outside function. You could find the general composition first, so then the general composition would be -x squared plus x plus 4. This is the general f of g. And now that we have a composed function, we can do a direct substitution of 2. So -2 squared. They didn't do it from highest to lowest. All right, I'll keep it their way. 4 minus x squared minus x. All right, keeping it together with this notebook. All right, so again, direct substitution. I start with the 4 minus 2 squared minus 2, and I'm not writing the squared because they have it right there. So 4 minus 4 is 0, minus 2 is -2. So we do end up with the same answer. So that part's good. So either you can start with the inside function, figure out the number it gets, figure out what the output is, and then put it into the outside function, or you can determine the overall general composition function and then just solve once. Up to you which way you do. Let's take a look at the opposite. What if we have g of f of -3? We take our f function, we put in 4 minus, and be careful here, -3. This is not -3. Anytime we do a substitution, we put brackets around the x. So 4 minus -3 gives us 7. Putting 7 into the function, we get 7 squared. Was it a plus or a minus? Plus 7. And now Ms. Gordon has to do mental math. 49 plus 7, that's going to be 56, is our final answer here. Okay, so this method used one substitution then the other. So we did the inside function, then we did the outside function. Determine and evaluate g of x means we're putting the g function into itself. So we're taking g, and instead of x, we're substituting the entire function again. So this is going to be x squared plus x all squared plus x squared plus x. And this is going to get yucky. Let's expand this. This is going to be x to the 4th plus x squared plus 2x x cubed plus x squared plus x. Oof, yucky. Okay, then we have x to the fourth plus 2x cubed plus 2x squared plus x. I think I wrote that in the correct order, and I think I collected like terms correctly. If I didn't, I'm sure you will be able to fix it for me. Okay, so if I wanted to know what is g of 1, I take my composed function and I substitute 1. Once you have the general composition function, you can do any of these. So 1 squared times 2, 1 cubed times, or plus 2, 1 squared plus 1. And this will give me what? 1 plus 2 is 3, plus 2 is 5, plus 1 is 6. Therefore, the final composition is 6. We could also work with composition and working with restrictions. So yesterday we did inverse functions and we looked at how not all inverses give us one-to-one functions or relations that give us, pass the vertical line test. So we had to impose restrictions. We're going to have to do something similar here because not all composition functions work no matter what we start with. So again, looking at two functions, we have a linear function and now we're working with a radical function. We know that radical functions require us to have a restriction, right? We cannot have negatives inside the radical. So determine the following. What's f of g, meaning f on the outside, g substituted inside? What is g of f? So starting with g, substitute f inside. Does the order matter? Pro tip, yes. I guess spoiler alert, and state the domain of each of the 4 functions. So the 2 individual ones and the 2 composed ones. So looking at A, f of g, we are taking the function f, the linear function, we are substituting g instead of x. So this is going to be square root x minus 3. So my function composed is this. Looking at g of f, starting with the square root function, substituting f inside. We are going to look at g on the outside, x minus 3 on the inside. So big square root. Actually, you know what? Let me do this in a different color, just so we keep everything separate. G of f means g of x minus 3. We're putting x minus 3 in to where we see x. So g of f is x minus 3, where they are on the inside. So does order matter? Let's talk about it in transformation language. If I look at the blue, right, this is a radical function that has been moved down 3 because that minus 3 is on the outside, right? That's our k value in our standard equation. If I look at this equation, the transformation that I see is right 3, a radical that has been moved right 3. These are not going to give us the same picture. So order does matter. These are not the same functions. They're not going to give us the same picture. Let's talk about their domains. So as a reminder, I'm just going to write this at the top of my screen here. F of x was x minus 3. Oops, don't need a bracket there. G of x was just the square root function. F of g of x was square root x minus 3. And g of f of x, I don't like this notation. It's got lots of extra bits. X minus 3. Okay, what is the domain? F is a linear function. Remember our catalog of functions here. We have a line and its domain is all reals. We have a radical. Remember what the radical looks like. Starting at 0, 0, sideways parabola. This has a domain of, oops, not all reals. X must be greater than or equal to 0. When I look at the domain here of f of g, this, again, think of a transformation, has been moved down 3. So if I were to draw this picture, I go down 3, there's my half parabola. The domain, my starting point in terms of going left and right, has not changed. So my domain here will be x is still greater than or equal to 0. The x is already written there. However, for g of f of x, I have moved to the right 3. So now I look at my standard equation and I've moved it to the right 3. In this picture, I do have a change of domain. Here, my starting point will be 3 or more, right? I've moved to the right 3. Another way that you can look at it is what would make this radical negative. I know that the radicand, the stuff on the inside must be greater than or equal to 0. Therefore, x must be greater than or equal to 3. So you can look at it from the transformation point of view. You can look at it from what would make the radical negative point of view. Either way, you can determine the domain. All right. Let us do some sketches. Let me just see how far we go here. Might not do all of these examples. This is quite a long lesson here, but I will do a couple of them. Let's go with determine the composition of two functions. All right. I'm going to do this one and this one. The rest, I would like you to try on your own. So we are given the function f is a quadratic. We are given the function g. It is linear. First question asks us to determine f on the outside, g on the inside. So I start with f. I put g inside. So anywhere that I see an x, I'm going to put brackets, and I put 2x inside the brackets. So this is going to be 4x squared plus 1 is the composition, and it says sketch the graph. Well, this is a quadratic. It has moved up 1, and I have a vertical expansion of 4. So up 1 is my vertex, and instead of going here to where the normal 1, 1 would have been, I have to have a vertical expansion of 4. So 1, 2, 3, 4. Have a very skinny, tall parabola. There we go. If I put f inside of g, then I take my g equation, 2x, I substitute x with the quadratic, that is f. I have 2x squared plus 2. I end up again with a quadratic, but now I have moved up 2, and I have a vertical expansion of 2. So vertex is at 2. And again, instead of the usual location of where 1, 1 would be, I have a tall parabola here. Again, we do have parabolas. They both have been shifted up. They're both have a vertical expansion, but they are not the same shape. They're not the same location. So it is important that we understand the difference. For a parabola going left and right forever and ever, the domain is all reals. And our range for the first one would be greater than or equal to 1. Wow, that bell is really ringing today. All right, for the green one, we have, again, all reals going left and right forever. The range now greater than or equal to 2. So slightly different pictures.